Okay, so in the last video we stopped here with the law of refraction and explaining why light bends in the first place, right? So just to recap, the speed changes, okay? The speed of light changes as the light moves from the air into the glass, in this case, right? So the speed will always change when it passes from one medium into another. And when it goes from a less dense medium into a more dense medium, the general rule is that it slows down. But if it slows down, okay, if it slows down, then that means either the wavelength or the frequency has to change. And because the energy of a wave is dependent on the frequency, if the frequency changed, then the amount of energy entering the medium would have to be different than the energy entering, or I'm sorry, the energy hitting the medium, right, would have to be different than the energy being transmitted into the medium. Now, of course, this is true in the sense that some of the light is reflected, right? Some of the light is indeed reflected, okay, so we do get this partial reflection, but between the amount that does get passed through, okay, so we're specifically talking about the amount that gets passed through. If energy were not conserved, then the total amount of energy between this refracted beam and the reflected beam would not equal the total energy that was in the incident beam. And so, since the speed of the refracted beam changes, it gets smaller, and the amount of energy or power that is transmitted into the medium, into the more dense medium, as a fraction of the total power that was incident, has to stay the same. And so that implies energy conservation. And so that means that the frequency has to stay the same. So the total number of wave fronts that pass a given point per unit time has to stay the same. And if that's the case, right, if that is the case, that the total number of wave fronts have to stay the same, that pass a specific point in time, then if the speed slows down, then the waves have to shrink. The wavelength has to get smaller. And so the only way for that to occur is for the wavelengths to get smaller, preserving the same frequency, is for them to bend. Okay? And that's why the bending occurs. So the law of the law of refraction has a pretty firm mathematical basis in a rule that we call Snell's Law. And Snell's Law involves trigonometry, so we're not going to give it to you here, but all you need to know is that for every two substances, the substance that the light is moving from, incident from, and the substance that the light is moving into, there is a strict mathematical relationship between the densities, or equivalently the speeds of light in those media, and the angles. And so this chart kind of gives you an idea. Here we have the angle that might be incident in air, and then the angle that would be refracted inside glass. Or alternatively, you can start in glass and then refract into the air. So for example, let's say that I have a beam that is incident at 30 degrees with respect to the normal in air, and it hits the glass boundary, and I want to know at what angle inside the glass the refracted beam is going to move with respect to the normal as well. So what I do is this chart, this yellow line, is derived from Snell's Law for these two media. And what I do is I say, okay, if my incident beam is 30 degrees, where is it going to be refracted, or at what angle is it going to be refracted? So I look at 30 and go up until it hits the yellow line, and I see that that happens at 20 degrees. So if I were to put a beam of light into a piece of glass that had this specific index of refraction, then the refracted beam inside the glass would be 20 degrees with respect to the normal. Now, one thing you'll notice, okay, there is a limit, because 0 degrees would of incidence would be that the beam is coming in directly along the normal. And if the beam comes in directly along the normal, then nothing would happen, right? As far as the beam being refracted, the angle won't change. So if I have a beam that comes in along this normal, the beam, once it's inside the glass, is going to continue just in that straight line. Now, it will be refracted in the sense that the frequency will not change, but the wavelength and the speed will. So the wavelength inside the glass is still going to be shortened. Okay, it's still going to be shortened, but the path will not deviate. Okay, and so that's what this point at the origin means. 0 angle of incidence means 0 angle of refraction, and vice versa. If I put a beam in the glass that's incident on the glass air boundary and refracts back into the air at 0 degrees, then it will also be refracted at 0 degrees. Okay, so that's what that means. But I can only get so large of an angle, so at 90 degrees of incidence would be equivalent to this. Let me pull this one up. Let's say I keep pulling this incident beam down, and such that it is moving right along the glass, right? Right at that point is going to be the maximum angle that I can put a beam from the air into the glass. And with that in mind, the angle of refraction, the maximum angle of refraction inside the glass, if the beam is incident from the air, is going to be about 42 or 43 degrees or so. Okay? And this kind of gives you a bit more of a visual of what's going on. So imagine that I have a normal right here, and it is perpendicular to this flat surface. And I have this incoming beam, and the incoming beam is 60 degrees with respect to this normal. Now, obviously, inside this glass, the beam has been bent, right? The path of the beam has been bent. And so if I want to find that, as long as I have a chart that gives me the index of refraction of the glass, then what I can do is say, okay, if I'm confident that this is a 60-degree angle between that beam and the normal, that would be right here, that's not shown. As a matter of fact, actually, let me put a normal on here, because I think that might be beneficial. So, right, there's a normal, right? So right about there, okay? So here's your normal, and this angle right here is the 60 degrees that we're referring to. As a matter of fact, let me extend this normal. Actually, let me do it this way. Let me extend this normal down in here, so that way you can visualize this. So here's the normal with respect to this surface right here. This angle is 60 degrees, and I want to know what this angle in here between the refracted beam and the normal is here. So I go to my chart, as long as this is for the correct index of refraction, and I start at 60 degrees, and I go up until it hits the yellow line, and I come over and I see that that's about 36 degrees. So this angle in here should be about 36 degrees. But then what happens when the refracted beam hits the glass air boundary again, right? Well, so here we can put another normal right here. We can just move this one along. So here we have another normal, and notice that this looks an awful lot like the situation we had up here. And as a matter of fact, it has to be equivalent, because if I start out at 36 degrees in the glass and I refract back into the air, I'm going to refract out at 60 degrees. And so even though the two beams, the incoming incident beam and the outgoing beam, are not going to be exactly in the same straight line, right? So if we kind of extend this, right? So this would be the path of the light beam if the block of glass were not there. But what you can see is that even though the outgoing beam, the path has been deviated, right? The original beam would have come here and the outgoing path is down here. These two beams are now parallel. Okay, so the beams will be parallel even though they won't be in a straight line. Now, this should beg a question, okay? So what if I send my beam inside the glass at a 45 degree angle, or I should say more than this 43 degrees. If I send my beam inside the glass at more than that 43 degrees, what happens? Okay, so the picture would be here. If my beam inside the glass is along the normal, nothing happens, right? The path of the beam is not deflected. But as I start to move outward, then the refracted beam in the air rather has a larger angle, and so eventually, right, I move it out a little bit more, I get an even bigger angle, move it out a little bit more, an even bigger angle. Eventually, the refracted beam is going to start to move along the plane of the boundary, right? As I sweep this angle out, this beam is going to adjust its angle in a larger increment for every angle increment that I move this beam out. So this refracted beam is going to start to move along the surface here before my beam inside the medium reaches 90 degrees with respect to the normal. And when that happens, when this situation occurs, when my beam is put at an angle with respect to the normal such that the refracted beam moves right along the boundary of the two surfaces, that is what's known as the critical angle. And any refraction, or I should say any situation where the light inside the more dense medium is incident on the boundary at a greater angle than that, then there will be no refraction outside of the medium. It will be completely reflected because now this part of the beam actually starts to move inside the medium, and when it does that, the only thing it can do is be reflected, and you have essentially a mirror surface. Okay, so where do we find application with this type of stuff? Where do we find application with total internal reflection? Well, one place we find some of this is in fiber optics. So fiber optics are little bundles of glass, and the glass has an index of refraction such that any beam that is incident onto the glass and puts light into the bundles, anytime it bounces off of a glass boundary, will be totally internally reflected. And so you don't get any light escaping outside of the glass fibers. And so this allows for extremely efficient transmission of signals and data. And that's why optical fibers are so popular with power companies and really things like internet. Anytime you have to transmit data, not just power, but data, right? So that's why optical fibers are used for internet substations and such. So that is the most common example of where we use internal total reflection. So that is going to conclude that section. In the next video, we are going to look at lenses and start to look at how refraction is used to correct eyesight. All right, so that's what we're going to do next. All right, we'll see you.